Hello, my name is David Waltzman and I'm a Senior Simulation Product Specialist with GoEngineer. This video is the first installment on a topic that we have previously ignored in our knowledge base. That's right, folks, I'm talking about sharks. Sharks have been around for hundreds of millions of years, way beyond humans, and definitely pre-SOLIDWORKS era. Sharks predate insects, mammals, and dinosaurs. Welcome to the evolution of shark anatomy, a CFD approach. One of the shark's greatest assets is its speed in the water. A major factor in this is its drag coefficient. This is the same principle that works for air flowing over an airplane wing or a car. We usually refer to something that is sleek as aerodynamic. In water, the appropriate term is hydrodynamic. Here we'll be analyzing a 20-foot great white swimming at 25 miles an hour. This is the maximum speed of travel and where drag will be the greatest. To analyze how shape influences drag, I created a configuration that has the same basic dimensions, but is prismatic in nature. To replicate the shark's environment, we'll use SOLIDWORKS flow simulation. To get started, let's dig into the wizard to define the project. Here we have the same shape, but now in rectangles and circles. So to dig into our wizard, we just go through, we define this as an external analysis because we're going to have water flowing over our body here. And the water is going to be rushing in this direction, which in this case happens to be our negative z. So we define our speed in here. Notice that we're in meters per second. So if I want to go back to my velocity, I could change my unit system here. So instead of meters per second, we're going to be in miles an hour. And go back through the end. So we're always flexible to adjust. And now we have essentially our flow simulation defined. So this large box is where we're going to be conducting our analysis. And now we'd want to define our goals for the simulation. So what we want to output from the simulation and where we want things to converge, how small we want all of our cells to be for the analysis. So if we load up our results here, my goal was on all these surfaces to look at the drag. And then I defined a cylinder where I'm going to refine the cells for my analysis. More interesting to look at here is the surface plots of the distribution on my model. So you can see that there's high pressure at the beginning here where the flow is hitting and rebounding and how it moves around on my model. The quantity that we're interested in is our drag force, which is about 55,000 newtons here. So let's pop over to another configuration that I have, and this looks more like that first model that we saw, but I've closed up the mouth and the gills just for ease of analysis. So now if we load up our results, we can look at that same surface plot, but now over these new faces, and it becomes more evident why the shark swims through the water much easier. There's a concentration at the nose, but again, that's to be expected because that's where the water is breaking. And if we look at our drag force, we're at about 9,000 newtons. This results in an 84% reduction in drag. As engineers and designers, we can only hope for and dream about such monumental increases in operational efficiency. Thank you for tuning in. This is David Waltzman from GoEngineer.